Hello, everyone. Thank you for joining us tonight. We'd like to welcome you to the United States Geological Survey Public Lecture Series. My name is Christy Ryan, and I will be your host and moderator today. Before I introduce our speaker, I do want to make a few announcements and hopefully allow others out there some time to get logged in. First, I want to give you a heads up about our lecture for next month. On October 27th, we will have the pleasure of welcoming Manuel Yuso, research statistician with the USGS. The title of her talk will be Blowing in the Wind, Science to Help Understand and Reduce Wildlife Impacts from Wind Energy. So please be sure to save the date and join us next month on the 27th as well. At the end of this lecture, I will provide information on how to join our mailing list, so you'll always be in the know about upcoming lectures in our series. Next, just wanted to take a minute to give you some tips on using this Teams live platform. One feature we definitely want to direct your attention to is the question and answer panel. That can be opened by clicking the question mark icon in the upper right-hand corner of your screen. At the end of the lecture, we are definitely going to open it up for Q&A with our speaker, and this is the panel where you can submit your questions. And feel free to submit them throughout the lecture. You don't have to wait until the end to do that. We'll do our best to answer everything that comes through, but depending on the amount, we may not have time to get to everything, so we appreciate your understanding in advance. One other feature we want to give you a heads up on is closed captioning. If you're watching this on a desktop computer, just look in the bottom right-hand corner for the closed caption icon. Another thing you can use is the stream text link, and that will give you live closed captioning as well. I went ahead and gave you the link to that in the Q&A panel. Now, I think it's time to begin our lecture for tonight. Tonight we have the pleasure of welcoming Robert de Groot. Robert is a physical scientist with our USGS Earthquake Science Center and is a member of the ShakeAlert Earthquake Early Warning System Operations Team. He's responsible for managing communication, education, outreach, and technical engagement throughout the states of California, Oregon, and Washington. His job includes recruiting technical partners who use the ShakeAlert system data to deliver alerts to people and to trigger automated actions like slowing trains. ShakeAlert is a people-focused earthquake early warning system. Robert works with over 30 social scientists from around the world to improve how people interact with the ShakeAlert system, with the goal to improve human safety. So enough of me talking. Let's go ahead and give a warm virtual welcome to Robert. Robert, the floor is all yours.
Thank you very much. I'm just going to go ahead and share my screen here. Let's see. Go. Screen is visible. You can hear me, right? Can you hear me?
Sounds good on this end.
Terrific. Well, good evening, everyone. I'm Robert de Groot. Thank you for joining us tonight. I wanted to start off with a land acknowledgement. From Pasadena, California, I want to personally recognize the lands of the Gabrielino Tongva Nation that I am currently occupying. We thank them for sharing these sacred lands with those of us who are newcomers. Well, welcome to ShakeAlert. All of you have done some kind of early warning in your lives. You've all done thunder early warning in your lives. You see a flash of lightning, and your eyes act as detectors, and your brain says, thunder is coming. You're processing that information. You brace for the noise that is about to come. You take some kind of protective action. That bracing is that protective action. Now, you may have had other experiences in dealing with lightning and thunder, right? You may have seen the flash and automatically a very, very loud boom. Everything happens at once. Everything I've just described to you is a warm-up for talking about earthquake early warning. One of the things I want to get across to you as well that's really important is that time is the basic currency of ShakeAlert. This is a very important piece. anything we can do to shorten the time between when we detect an earthquake at the surface and when people get alerts on their phones is what we're after. Now, before we get started, an earthquake could happen during this presentation, and we want everyone to be safe. So if you feel shaking, or if you get an alert, drop cover and hold on. If you'd like to follow us on Twitter, we're on at USGS_ShakeAlert. But if there is an earthquake, do that after you drop cover and hold on, please. We're coming up on the annual Great Shakeout Earthquake Drill on the 20th of October at 10:20 a.m. And in the states of California, Oregon, and Washington, there likely will be some test alerts delivered to cell phones, and more information will be forthcoming, especially if you already subscribe to those apps. So consider doing a ShakeAlert powered shakeout drill on the 20th of October. If you'd like to learn more about Shakeout, visit shakeout.org. And also register for the drill so that you can be counted among the millions of people who participate every year. I have 4 major takeaways for you to get today from this talk, and I'll cover a lot of details. I know that some of you are really interested in the earthquake that happened near Santa Rosa last Tuesday on the 13th of September. And we're going to do a short case study at the end of today's presentation, and everything that I talk about will get you ready to do that case study. So, and I'll also review some of the stuff as well, but we are going to cover a real event and kind of talk about it in context. 4 major takeaways. Number 1, partnerships is our superpower. This is actually a quote from the new director of the USGS, David Applegate, who coined this phrase during when he was basically made official as the director. And this is actually true for ShakeAlert. It always has been true. We are a very large community of partners from across the West Coast and other places around the world. The 30 social scientists that was mentioned in the introduction come from all over the place. But we would not be here. ShakeAlert would not be what it is if we didn't have all of our partners from across the 3 states. And I've listed the logos at the bottom. We are in the middle of building an earthquake early warning industry. And what's really important here is that we are still in this process of working with very creative people who really want to keep people safe. And we are looking for new partners to help us deliver alerts to people and also to set in motion automated actions. So we depend on these technical partners to provide what we call ShakeAlert powered products and services. And I'll cover more about this later. But we are on a mission to expand and really to grow this as quickly as possible. We are a people-focused earthquake early warning system. We now protect over 50 million residents and visitors to Washington, Oregon, and California. And we want to optimize how people interact with the ShakeAlert system. So, as was mentioned in the introduction, we're doing a lot of social science research. And we're working in topics in areas such as messaging. What does the alert message actually say? It's got to be short enough, and people have to be able to understand what it means and to take some sort of actionable steps to protect themselves. We want to really minimize the amount of time that it takes people to process when they get the information and what they actually do. So we're looking at everything. We actually are getting a lot of really interesting closed circuit television information, and there have been several earthquakes in the last week that have provided much more data for us to see what people do when they feel shaking. And this is really helping us understand how to best educate people on what to do when they feel shaking or when they get a ShakeAlert powered alert. What's really important to us, though, is in the middle of this slide, earthquake early warning for all. This is our vision. We're studying and applying what we know so everyone has access to earthquake early warning. takeaway number 4. ShakeAlert is one tool in a very large earthquake risk reduction toolbox. Now, hopefully, if you live in earthquake country, or even if you don't live in earthquake country, you've put together disaster supplies kits or emergency supplies kits. And in the case of that, you know what to put in there. You have a toolbox. We also have an earthquake information toolbox as well. And this is part of what's shown here is a collection of advanced national seismic system earthquake information products and tools. It's a collection of earthquake information products that are accessible so that you can get information about earthquakes. Notice the timeline from years before to many minutes after the earthquake. And what's really important to notice about this is that ShakeAlert is first out of the gate. It's information produced by the ShakeAlert system is produced within the first few seconds after the earthquake is detected at the surface. And what the ShakeAlert system generates is called a ShakeAlert message. And the ShakeAlert message contains a few components. One of them, it tells us where the quake happened. And second, how big the earthquake was. And third, how much shaking that could happen around that quake. And what's critical is that this is an estimate. This information is produced super fast. So the ShakeAlert system and all the people who work on all the under the hood components of the system have struck a very important balance between accuracy and speed. As I said, our basic currency of ShakeAlert is time. Now, what's really important here, though, is ShakeAlert is not the cure-all. All of you probably know what to do if you feel shaking, drop cover and hold on. And you should still continue doing that. ShakeAlert is another tool in the toolbox. It could give you the potential of getting some seconds of warning before shaking arrives at your location. And in those seconds, you can do a lot. It doesn't take long to drop cover and hold on. But what's important to realize is that all of these tools play a role in reducing earthquake risk, basically making you safer. The question arose at some point is, why did we choose California, Oregon, and Washington to build the ShakeAlert system? And the reason is that these 3 states have the highest earthquake risk in the country. And so the USGS is committed to completing the ShakeAlert system in these 3 states first. And we're pretty close to finishing off the construction of the ShakeAlert seismic network. We're about 80% complete. I'll talk a little bit more about that later. But we are committed to finishing in these 3 states first. A little bit about the history, about the background of earthquake early warning and where it is today. Earthquake early warning is not a new idea. It actually has been an idea that's been around since the 1980s, and a lot of people at the California Institute of Technology here in Pasadena and at UC Berkeley and other places around the world have been thinking about this idea for a really long time. Starting around 2006, we started working on what we call earthquake detection algorithms. And this is basically the under the hood components. It's the mechanics. It does the earthquake detection and does the calculations super fast. And these algorithms are actually continuously being improved. In fact, the one statement we can make about ShakeAlert, it's in a process of continuous improvement. But we want to make sure that we have an operational system so that we can keep people safe. So in 2019, we rolled out, as the term is, public alerting to cell phones in the state of California. And then 2 years later, the states of Oregon and Washington began their public alerting campaigns. And in 2025, as I mentioned a little bit earlier, we are completing the build out of the ShakeAlert system seismic network, and I'll show you some pictures about that in a little while. So the question is that, well, let's actually find out how the ShakeAlert system works. I think that's important here. And so let's step through the process. And I want you to notice the flow chart in the middle of the slide. And don't forget about the red circle for a second, but follow from left to right. And the first thing that has to happen is the earthquake has to be detected at the surface. So we use a sensor network, seismometers, to do that. We move that information super fast from the field to one of 3 processing centers. And on the far right, there's a map of the 3 West Coast states. We have a processing center here in Southern California, another one in the Bay Area, and the third in the Pacific Northwest. That information is then processed. These under the hood algorithms that I mentioned earlier produce these ShakeAlert messages, which contain these estimates of location and size and the shaking intensities. And then the system makes that information available so that our delivery partners, a critical piece of the equation, are able to take this information and alert people and also trigger automated actions in systems. So the flow arrows at the bottom, the arrows at the bottom of the diagram, bottom of the slide, show what the USGS does and what our technical partners do. This is a very, very important piece of the puzzle. We really need technical partners to help us get the alerts and to trigger the automated actions. This is a big piece of the operation. So let's start a quake. Earthquake begins at depth, and we're going to talk specifically about the Santa Rosa earthquake in a little while, but the earthquake happens at depth. And it takes a little bit of time for those seismic waves to reach the surface, and the amount of time that it takes is related to how deep the earthquake is. What reaches the surface first is something called the P wave, and it's traveling about 4 miles per second. And when it reaches the surface, the seismometers pick it up, and that's when the ShakeAlert system swings into action. The goal is to detect that earthquake as quickly as possible using those very first seismic waves, because what will follow are the waves with heavier shaking, the S waves, which travel about half the speed of P waves, so about 2 miles per second, and then the waves that follow that, the surface waves that also could cause more shaking. And the little animations at the bottom show how P waves and S waves move through the earth. If you clap your hand, you've just produced a P wave. What happens is the air is squeezed and stretched, and that's what's passing through the earth. Rock is being squeezed and stretched, reaches the surface, seismometers pick it up, and that's when all the action starts. So we need sensors on the surface to be able to do this, and this is something that I mentioned a couple of times already, and I'm going to play a small animation on the right that shows the build out of the sensor network between January of 2015 and the end of 2023, the projected build out. Because I mentioned earlier that we would be finishing off completing the seismic network build out by the end of 2025. And I show a little table here on the left, giving you a sense of where we currently stand. Across the West Coast, we're about 82% complete, California 81%, and in Oregon and Washington about 85%. So we're making really good progress, and the system is performing really well. And what happened last week in Santa Rosa is a really good indication of our successes. So we get to the step of actually detecting that earthquake and moving that information to one of the 3 processing centers, the red triangles on the right. So what happens next? That information, of course, the computers chew on it. It's all really fast. To give you a sense of how long it takes to produce a ShakeAlert message, it's in a matter of seconds. It's very fast. And so this is an important piece because, again, we're trying to shorten the time between when we first detect the earthquake at the surface and when we get information to you. So the ShakeAlert system must be completely automated. And what's really important about this is that the system produces the ShakeAlert message on its own. But we need someone, we need a person, we need a human being in the loop to check the system. So what happens when that ShakeAlert message is published? We have a team member, one of our operations team members is up and gets up in the middle of the night if necessary to analyze the information that came through the automated system and ultimately press a button that confirms what has happened or not confirm what has happened. And this is all done within minutes after that message comes through the system. I just want to point your attention to a couple of the diagrams here just to give you a sense of it, and then I'll actually cover this a little bit later when we go through the case study. This summary report are the numbers that come out of the ShakeAlert system, and it tells us a little bit of information of what happens. So the key thing here, though, is you see ShakeAlert messages issued after origin time. Origin time means when that earthquake began at depth. So we don't know the earthquake is happening until it reaches the surface. The critical piece here is that time is included in this number. And when I talk about Santa Rosa, I'll go back to this and say, well, really, the ShakeAlert system did its thing much faster than it shows here. Another piece that I want you to look at as well is the ShakeAlert system isn't done once it issues that first ShakeAlert message. It actually monitors that earthquake in real time. So it's possible that updates to this information could happen up to 2 times per second. Now, we only show 3 here because there's only a limited space for information, but it does give you some information. And actually, when we talk about the case study, you'll see how this evolution in time of the earthquake led to additional alerting to people in Northern California. If looking at the numbers here, the first ShakeAlert message was published, was issued at 4.5 seconds, and that initial magnitude estimate, keyword estimate, was magnitude 4.9. And then as the earthquake progressed, and literally like half a second later, the estimate was magnitude 5, and you can follow the rest down the path there. Now, this particular earthquake ended up only being a magnitude 4.4, but we'll get at this point a little later about this trade-off between accuracy and speed. It's really important. In the diagram in the middle, you'll notice that there are some octagons, and those octagons, actually, the color of them actually correspond to shaking levels. And I'll show you a diagram a little later that will give you a sense of what those shaking levels mean. But what I want you to notice is in the lower left-hand corner of the diagram, you'll see a piece of a very large octagon. You actually see it up in the upper right-hand and upper left-hand corners as well, of a much bigger octagon. And we call these alerting contours. Now you must be asking, well, why did we choose octagons? Why didn't we just make circles? Well, it turns out that this particular geometric shape is that balance between speed and accuracy. If we try to make a circle out of it, it takes a really long time. And it's that octagon is actually that sweet spot between speed and accuracy, and that's why you'll see those. And all of you will be ShakeAlert powered by the time we're finished today, so you could actually look up this information yourselves. So once that ShakeAlert message is published, what happens to it? It's made available to our technical partners, and they make use of that information. Also, what happens, and I mentioned this earlier, is that we have that 24/7, 365 duty officer who's analyzing the information and presses a button at one point, basically providing a confirmation. And what you will see for earthquakes that are magnitude 4 and larger, in California, Oregon, and Washington, you'll see this particular tile show up on the screen of the event. And if you get to the page with current earthquakes from the USGS, you can look up these events. It's in a list, and you'll see this particular picture appear on that event screen within about 10 minutes after the earthquake, and usually faster. And when you click on that, you'll get a lot of the most of the information, actually more of the information that I've explained. You'll get to that information, you can get at it yourself, and you can do some interpretation, which is kind of fun. So alert delivery, ShakeAlert powered alert delivery happens at different levels. And we've worked very closely with our partners throughout the 3 states and with other parts of the federal government to decide what is the best levels to deliver alerts to people and trigger automated actions. And what you see here on this slide is actually the result of that. And I'll give a couple of examples in a second. But one thing that triggers, or one of the key pieces of this, is the magnitude threshold. And we go down to about magnitude 4. So alerts, ShakeAlert powered alerts can be delivered starting about magnitude 4. And usually those are applied to things like slowing trains or closing valves or opening firehouse doors. A lot of these are automated actions. But we work with our technical partners to make some decisions. So for example, at this magnitude 4 level, we could, a classroom, a school, a PA system could go off telling the students, faculty, and staff to drop cover and hold on. And if we go up the list, you'll see we get up into the realm of alerts being delivered to cell phones. And we'll talk a little bit about that here in a second. But and I'll explain kind of how it works out. But the colors you see here on the right with the intensity thresholds, this is amount of how hard the ground is going to shake. Those colors actually correspond to the octagons that you saw in the last slide, and that's a really important piece. And the thresholds of delivery, I'll give you a couple of examples here in a second. But this is the modified Mercalli intensity scale, of course, going from 1 up to 10 plus. You can see things get progressively worse as you start at 1 and go all the way up to 10. Most of the action that happens with ShakeAlert and alert delivery happens around the MMI3 and MMI4 areas. So in the cases of MMI3, it's generally weak shaking, and MMI4 is light shaking, and you feel different things, and there are a lot of factors on depending on what you feel that influence what you feel. But we do most of our alert delivery in the MMI3 and MMI4 range. So let's use a couple of examples. Let's talk about the wireless emergency alert delivery, or WEA as it's called. If you've ever gotten an Amber Alert on your phone, or a severe weather alert, or even several COVID alerts were also delivered on by WEA. This is a system that's used, that's actually managed by the federal government, and the USGS has a direct connection to it. It's our one way of knowing that we can get alerts out to people if everything else we're not to work. So we want to have that backup, and a lot of things about ShakeAlert is having a plan A, plan B, plan C in place as well. So we want to make sure we get the alerts out to people. So let's talk about what happens for wireless emergency alerts. First of all, the purpose of wireless emergency alerts is to inform people of imminent danger. That's a very, very important piece. And so we only want to distribute alerts to people when they know, when they may feel shaking that could hurt them. So this is the way it works. So in the case of WEA alerts, the magnitude threshold is magnitude 5. That means that WEA alerts will not be delivered, the delivery will not start until that earthquake is magnitude 5. And the key word here is estimated to be magnitude 5. So the ShakeAlert system must estimate that earthquake to be magnitude 5 or larger to start the delivery of those WEA alerts. Now, who is going to get those alerts? We're just not going to send them to everybody, but we want to make sure the people who need them the most get them. So we start sending them to people within that MMI4, that Mercalli intensity 4 region, and that's that one octagon, and I'll come back to it again when I talk more about Santa Rosa. But that's the people in the MMI4 and greater region will receive those WEA alerts. We want to make sure the people who really need them get them. If you have a cell phone app and you are, you have it running, you will get alerts as well, but it's a little bit different. The alerts start being delivered to cell phones starting at magnitude 4.5. Now, who will get those alerts? If you happen to be in the MMI3 or greater region, you will get those alerts on your phone. So this is considered to be weak shaking. So MMI4 is light shaking, MMI3 is weak shaking. So what will happen is if that earthquake is estimated to be magnitude 4.5 and larger, then you will, and you are in the MMI3 region or greater, you will get alerts on your phones. Now in that diagram I showed you, you notice the MMI3 region went off the map. You could just see the edges of it. So everybody within that area would have gotten an alert on their phone if you had a cell phone app installed. I talked about plan A, plan B, plan C. Our motto, or one of the phrases we use, is by every pathway possible. And so we try to get alerts by as many pathways as possible. So it's a good thing if you get 3 or 4 alerts on your phone, or if you happen to be in a school building or on a train and you get an alert and the train also slows down. We see no problem with that because we want to make sure that you stay safe. So any way we can get you alerts, and if it's more than one, that's a good thing. 3 major technologies have been used for public alert delivery. The first one is cell broadcast, and we talked about this already. The wireless emergency alert system uses cell broadcast technology to make this happen. So what basically happens if you're within the footprint of a particular cell tower, and that cell tower happens to be within the MMI4 region, then those alerts will be distributed by that cell tower to all of the people who happen to be in that footprint. So cell broadcast just basically blasts the message out to everybody in that region, and this is by design. The second one is something called call push notifications, and this is an alert delivery technology which is in common use. If you get something that pops up on your cell phone saying that so-and-so is now following you on Twitter, or a news blast from CNN or something like that, this is a push notification that comes to your phone. Same thing happens with apps, is that you'll get these push notifications that will be delivered to your phone. Now, a critical piece to this, though, is that in the case of WIA, it's just sent out by the cell tower. The difference with push notifications, of course, is that the cell phone app needs to know where you are, where you're located. So this is where the issue of knowing, of having your location services on, and basically they'll have a sense of where you are. And if you're in that MMI3 region or greater, you'll get alerts on your phone. And lastly, broadcasting. Again, this is a technology that doesn't depend on the same technologies as the previous ones. Broadcasting alerts can be sent out over television frequencies or even FM frequencies. And actually, we do have some partners who are working in those regions. We have one partner who's actually actively selling equipment where you can receive ShakeAlert power alerts using FM frequencies. I've been talking a lot about getting alerts to your phones, but there's a whole host of automated actions that are powered by ShakeAlert. And I talked a lot about automated actions that alert people through your cell phone and others, but also getting alerts over PA systems. But on the right, there are machine-to-machine actions like slowing those trains, recalling those elevators, opening the firehouse doors, all of the different pieces. Again, they both work together. And what's really important about the automated actions that are machine-to-machine is they happen without human intervention. All of this has been set up ahead of time. So a lot of these things, like slowing down that train, it's going to happen automatically. No one has to intervene to make it happen. So if you want to get alerts on your phone, you can go ahead and scan the QR code over on the right, and it'll bring you to a USGS webpage where you can figure out what you want to put on your phone, pick which one you want, or all of them, whatever you want. If you can't read the QR code, the link at usgs.gov/ShakeAlert, you can get to that same page. And over on the left, I just talk about the variety of ways to get alerts on your phones. All of this information is on the web page, so it's not necessarily important you see it here. One example I want to give, though, is the emergency alerts, that message at the top. This is what you will get if you get a ShakeAlert powered WIA alert on your phone. It's very short. It's like 90 characters long, and we were limited to 90 characters, and it was kind of fun to make an alert message that was within 90 characters, but we get the essential pieces across. This message covers all the bases. It tells people that what's going on. An earthquake was detected. It's telling you what to do. It's also telling you to do what you're doing, to do what you need to do immediately. And that's a very important piece. What's critical about this message is it tells you what to do. There's an actionable piece to this. And it also tells you who the message is from. And that's a pretty important piece because you want to make sure that it's coming from a credible source. So it has all of those elements. So let's talk about the Santa Rosa earthquake. You've seen these pictures before, and so a lot of this is sort of old hat for you. What's really interesting about the earthquake that occurred last Tuesday at 6:39 p.m. Pacific time is that over 400,000 people in the Bay Area received alerts on their cell phones. And this information, of course, available on the web page. Now you may be asking yourself, well, wait a second, that earthquake was a magnitude 4.4. What's going on? I'll get to that in a second. Look at the picture again on the right. Notice that the light blue is the MMI4 region. So remember MMI4, that alerts within that MMI4 and greater, WIA alerts were delivered. And outside, you see the edges of it, cell phone alerts. That's the MMI3 region, the larger octagons. So just remember that for reference. So let's talk a little bit about this estimate piece here. So I mentioned to you that the first ShakeAlert message is issued once we detect the earthquake and we're able to process the information. And that happened in 4.5 seconds. Now that's pretty fast, right? But there's something else to consider here, is it took about a second for the seismic waves, which the earthquake started about 5 miles under the earth. It took about a second for that earthquake to reach the surface. So really, ShakeAlert did what it did in less than 4 seconds. So the first ShakeAlert message, the processing time was something like 3.5 seconds, which is pretty important to remember. Now, okay, so what happened is about a half a second later, the ShakeAlert system did a second measure, did a second sampling of the earthquake, and the estimate was magnitude 5. So what happens at magnitude 5? That's when the WIA alerts start being delivered. So the first initial ShakeAlert message, that's when cell phone alerts went out, but then when that earthquake grew a half a second later, the estimate grew to magnitude 5, that's when the WIA system was triggered and the WIA alerts went out to everybody within that MMI4 region. So that's basically the way the process happened. And of course, the final number about 14 seconds after the origin time, the magnitude went back down to magnitude 4.6. Now you see to yourself, well, okay, but this earthquake ended up being magnitude 4.4. Well, that information is collected over time. And the way I like to think of it is that you've heard these stories. If you have a picture of a digital picture that has a very low pixel density, and it's sort of, with very few pixels, you kind of have a shape and you don't know what it is. And you keep adding pixels, you keep adding pixels, you keep adding pixels, and it turns out to be a picture of your dog. And that's what happens over time with earthquakes, is that we get more and more information about that event over time. So first of all, we made these estimates within seconds after the earthquake was detected, and it took a little while, and finally that number came down to 4.4. But the difference between this, it's that balance, as I said, between accuracy and speed. Now, of course, as time passes, I mentioned things like shake maps, the other tools on that timeline that I showed you earlier. Other tools like the shake map is published. This happens minutes after the earthquake is over. Everything happening with ShakeAlert is seconds after the earthquake. So you can go back and look at all these other information pieces, and everything will be laid out for you right on that event page. Those event pages are full of all kinds of information, so you can get all kinds of things out of it. So I mentioned earlier that we are looking for creative ideas, and this is a little bit about the process, about how you can come up with a new idea and bring it to fruition, bring it to actual application. And we've had many success stories over the last 6 years in people coming up with what they may think are maybe sort of strange ideas, but those strange ideas actually lead to innovation. So there's this element of having technical savvy, but there's also the creativity that goes along with this. So that's a very exciting part of ShakeAlert, is the amount of creativity that goes into this. Being a people-focused earthquake early warning system, we want to make sure that people can use the system, that we optimize the human interaction. So everything that we develop, and I do a lot of work with development of educational resources and everything else that connects people with the ShakeAlert system, we want to make sure that all of the stuff is accessible and it's also inclusive. So we want to make sure that we're thinking about colors and about language and those sorts of things. And we have most of our resources are translated into several languages, and you've been seeing the Powered by ShakeAlert stickers, the oval stickers, throughout today's presentation in different languages. And so that's one thing that we're doing. We also want to make sure is that we're the USGS. We want to make sure that things are scientifically accurate. And so we want to make sure you get the right facts. So we spend a lot of time making sure that we're getting the right scientific information out there. We want to make sure that what we develop can be used by all of our partners. We work very closely with our 3 state emergency management agencies to get the word out about ShakeAlert. So we want to make sure that they can use that information as well. And one way of doing this is by combining what we do with other programs and projects like the Great Shakeout. We want to make sure that we have input from our partners. Again, ShakeAlert is a collaboration across 3 states. And so we want to make sure that we're working with our team members, that it's something that they can use and that they have a word and they can take ownership of it. And I mentioned the alignment point earlier. So these are just some samples of our resources across. We of course have focused on some critical sectors. One of the things is that after an earthquake, there's certain critical sectors that are really important to us, things like transportation and utilities and healthcare, things that are going to matter very much after an earthquake. So we want to work very closely with these groups that's not the only groups we work with, but we want to make sure that they have a good understanding of these issues, how to communicate them, but also how to get ShakeAlert integrated into their facilities. You've seen some of the other graphics that we've produced these in a variety of languages. You've seen several of these throughout today's presentation already. We have also finished a third year of what we call our messaging toolkit. So what I showed you in the last slide was something we finished during year 2. And we've put a lot of focus this year on diversity, equity, and inclusion to make sure that the ShakeAlert system is accessible to all. Again, our vision, earthquake early warning for all. And so here, a colleague of mine, Mariah Jenkins, is giving an introduction to our guidebook that talks about access and functional needs and making ShakeAlert accessible to all. And so it's an example of some of the illustrations and some animations that we put together in this area. On the left, we've also done a lot of work in really streamlining the process to make sure that those people with those brilliant ideas about how to use ShakeAlert messages for new and interesting applications can go through the process from basically getting from their ideas, the light bulb above their head, to where something is actually implemented in the real world. I mentioned earlier about aligning ourselves with other programs, the 7 steps to earthquake safety, working with organizations like the Earthquake Country Alliance and the Great Shakeout. We've integrated earthquake early warning into the 7 steps. And so step 5, of course, it used to be drop, cover, and hold on when the earth shakes, but now we've modified it when the earth shakes or when you get an alert. And notice the drop, cover, and hold on, and we've done a little bit of a different with our illustrations to meet sort of our branding and sort of our own identity, but we're telling people to do the same thing. In fact, one of my colleagues from the Los Angeles Unified School District says that ShakeAlert asks you to do what you already do, but do it sooner. Please follow us on Twitter at USGS_ShakeAlert. We talk about what's going on in our community. We highlight partners who are using ShakeAlert in their facilities, new ways of getting alerts to people. We also get online after earthquakes that involve the ShakeAlert system, and we'll start tweeting about it. So this is actually the tweet from the magnitude 4.4 earthquake in Santa Rosa last week, and we got this up within about 10 minutes after the earthquake. Included the shake map and also information, and this tweet thread is actually quite a bit longer. We also want to make sure that we have lots of resources. We want students to use ShakeAlert as one of the most amazing examples of science, technology, engineering, and mathematics, or STEM learning. So a lot of resources that are developed with our partner, the Incorporated Research Institutions for Seismology. They've helped us develop all kinds of animations and all kinds of activities. We're also working with another organization called UNAVCO, who's helping us with the integration of new technologies into the ShakeAlert system coming soon. And also, we're very interested in our youngest partners, our youngest people, knowing about ShakeAlert and how to stay safe. And so we've worked with our friends at the Hero and You Foundation to develop a booklet called Rocket's Earthquake Safety Activity Book. Of course, there it's translated into Spanish, but we have this booklet in about 9 different languages, including Armenian and French and Korean, lots of different languages. And so there's ways to get at those resources as well. With that, I'd like to thank you for being here today. Thank you for joining us for this ShakeAlert success story. I'd also like to give a shout out to all of my USGS colleagues, people who I work with every day. Of course, the ShakeAlert operations team, who's tireless in their work here every day and also responding to earthquakes 24/7, 365. I'd also like to give thanks to all of my USGS colleagues in Scientific Information Services, in the Office of Policy and Analysis, and others who help us with every aspect of what we do with ShakeAlert. USGS as a whole has really contributed in so many ways to the success of the ShakeAlert system. And I'd like to thank you for joining us tonight and thank all of my colleagues for all of their great work. Thank you.
Wow, thank you, Robert. That was a lot of really good, really important material. And I live in the Bay Area, California. I've lived here my whole life. We've been through the Loma Prieta event of 1989, so I understand just how important this ShakeAlert program is. So I've been monitoring the questions that they've been coming through. We've got a few really good ones here. So let me read the first one. This one is from Ron, and he says, the earthquake near Puerto Vallarta, Mexico recently caused water in the cave in Death Valley, to have fairly significant wave action. That was over a distance of many hundreds of miles. Can you share your thoughts about why that happened so far away, and how does a major earthquake 1,000 miles away or more increase our risk of an earthquake here? Does it increase the likelihood or decrease it? And he also sent a link to a video on it, but I think you get the gist of his question there.
If you've ever stood next to a car and you hear kind of boom, bada, boom, bada, boom, bada, boom, bada, boom, bada, someone has their radio on and you hear the very long waves coming from the car. If you were inside the car, you could hear all the music. That's basically what's happening in this case with the earthquake in Mexico and the earthquake in, or excuse me, the wave action in Death Valley. So it's those very, very long wavelength waves from earthquakes that are able to travel much longer distances that can affect things. And it's the same case if you use the stereo in the automobile analogy. It's the same sort of situation. It just turns out that the metal and all the other materials in the car are really good at filtering out all of the very short wavelength sounds, radiation from basically radio waves or sound waves. The short wavelength stuff gets filtered out very fast, and what gets out is the very long. So it sounds like the car is basically vibrating. That's basically what you hear. As far as your question about earthquakes affecting one another, so making those connections between earthquakes very far away from one another is something that's still a developing area. There's a lot of work in this area. Of course, we know that the Earth is a single system and things affect one another. There have been some cases, and there's an earthquake in 1992 called the Landers earthquake, which had an interesting sequence starting on April 23rd or 24th of that year, where there was a series of earthquakes that could have influenced each other, an effect where one could potentially have set up the conditions for the next one. As far as something as far away as Mexico, potentially setting something off in California, the evidence doesn't appear to be there yet. But of course, this is why we do earthquake science. This is why the USGS is so committed to this work, and so many other people in universities, to really understand these really interesting potential connections.
Okay, great. Just a reminder for everyone, you can submit a question for Robert, clicking the question mark icon in the upper right. That's the Q&A panel. Okay, here's another one. You may have gone over this. This came in fairly early. How do you determine, this is from Bob, how do you determine who alerts go to? Is there a certain radius or miles need to be away from the event to get them?
Yes, and so I'll go back to a slide here that actually hopefully will help. I have to be careful because I can't just simply jump through. Oh, right here. So this is really what you're looking for. And so the estimates from the ShakeAlert system tell us who should get alerts. And so these estimates, these polygons, or they're octagons, and those define the shaking levels. And the shaking levels, depending on, it depends first on the magnitude of the earthquake, but then once that magnitude of the earthquake triggers the alert delivery for that particular approach, alerts will go to people inside of that. So in this particular, let's use Santa Rosa as an example. That you see the very large octagon, which is on the edges. If you were inside of that octagon all the way to Santa Rosa where the star is, you potentially could have gotten an alert on your cell phone from an app. If you're inside the light blue octagon, MMI4, and into the star, you could have gotten an alert from your app, and also you could have gotten a wireless emergency alert. So what we provide in our ShakeAlert messages is information about where earthquake alerts should be delivered or could be delivered. We provide them with the raw information, and based on the threshold diagram that I showed you earlier, the decisions are made who should get alerts. And the critical piece here that I mentioned that's really important is that it takes a lot of work to get alerts out to people. It takes a lot of orchestration and coordination. So one of the important parts about alert delivery that that all people should be concerned about is that we want to make sure that people who should be getting alerts are getting alerts. So that's one of the reasons why we focus on getting wireless emergency alerts to people in the MMI4 region, in that light blue octagon and greater, because they need it the most.
Great. Another one that came in here, and if you like, we have an FAQ on this I can add. The question was, how do I sign up for ShakeAlert?
please visit usgs.gov/ShakeAlert. There is a link there that will take you to a page that you can sign up, get alerts on your ShakeAlert power alerts on your phone, and there are a variety of apps and ways that you can get alerts. If you have an Android phone, there are additional ways you can get alerts, but visiting us on that page at usgs.gov/ShakeAlert will get you to a page that will allow you to make decisions about what you want. You can get one or you can get them all.
Great, and I did put that link in there.
Oh, thank you.
For folks, yeah. So that's in the chat. Here's another question. What's the point of the manual audit by duty officer? Does the actual alert not go out until he or she approves?
That's a really good question. And what'll happen is, again, the automated system is going to publish that ShakeAlert message, it's going to post it, and it's going to get used and stuff is going to be moved down the pipeline. So nothing slows down the ShakeAlert message. The role of the duty officer is to make sure the system is doing what it should be doing. We believe that there should be a human element there to analyze that information to make sure what's going on is going on. And if there's something that happens that is maybe not quite what we expected, we're able to do some interpretation around that. And so one of the things that could potentially happen, and this is actually a case that happened I think it was last night or 2 nights ago, there was an earthquake off the coast of Petrolia off the Redwood Coast in Northern California. And the earthquake estimate was one size, and the earthquake actually ended up being a little bit smaller. It turns out that earthquake was slightly mislocated. So remember, we're doing location determination and size and shaking distribution and the intensity very fast. So if the earthquake location is a little bit off, that could potentially change who gets alerts. The purpose of that duty officer is to analyze that information so that we know what to do for a response. So let's say alerts were delivered to a large population that we didn't expect. We know how to deal with it and how to message that, but also how to get the right information to people to let them know what happened. A critical piece is in doing earthquake early warning is really interesting sort of endeavor because we're connected to the people all the time. So we want to get you the best information possible. So having a person there who's actually watching the system and understanding what it does and how it works and knowing the under the hood stuff, it's like a car mechanic that's on duty all the time. They can help us understand what happened. And also, as I mentioned earlier, we're in a state of continuous improvement. And so by monitoring these earthquakes by a human being, they're able to help us learn the lessons to improve the ShakeAlert system.
Yep, all makes sense. A few more questions. When I get a ShakeAlert, it sounds like an Amber Alert. Is there a way to change the sound?
That's a really good question. That's the future. And so what we want to do, as I mentioned, is the basic currency of ShakeAlert is time. And we want to lessen the time between when we detect the earthquake and when you get the alert and when you can do something with it, right? It's really important. And right now, everything that comes through the WIA system has the same sound. So what you have to do is, let's say your cell phone is in your backpack or your purse. You have to pull it out to find out, well, what is that all about? And so one of the things that we really need to do is, and we're working on, is to develop a unique sound that you identify with a ShakeAlert powered alert that comes on your phone. So you don't need to look at the phone, you hear the sound and you practiced, because this is the idea of doing shakeout, is to practice. So you practice what to do when you get that sound and take that protective action. So yes, that's one area that we're working on. In fact, it's one area of research that we're actively pursuing.
Great. This question, I'm still going to ask it, but they answered their own question because you went over this in your talk. They said, so no alerts happen for MMI size and above, and then they answered that for themselves. I don't know if you want to comment on that anymore.
Yes, and what's critical is that if you again look at the map here on the right, is that everybody within the outermost octagon, you see this, the blue here, everybody there right to the star likely got an alert on their phone from an app. Okay, so that whole large population, and we talked about the large numbers involved. If you look at the MMI4 octagon, the light blue one, that's basically everybody inside of that and to the star received a WIA alert. So it's everybody who could experience that shaking or higher, and that's a critical piece. If you're going to feel that, if it's expected that you'll feel that shaking or larger, you'll get that type of alert. In the case of the MMI4, everybody inside of there could have gotten a WE alert and alerts from apps.
Okay. Another one here from Anonymous. Who would I report false alerts to?
Well, that's typically if something happens and we call a false alert, I mean, we would likely know about it as well. I mean, certainly you're welcome to reach out to us at ShakeAlert if there is something that you got that you shouldn't have gotten. And this is part of the challenge, right? In terms of doing very quick alerting, is that if our location is slightly off, that could lead to a different estimate about earthquake size. It could also translate into some people getting alerts that shouldn't have gotten them. You're welcome to reach out to us, but typically we know it happened when it happened, and we'll generally talk about it on Twitter and other channels just to say, this is what happened. If you got an alert and you didn't feel shaking, which happens, and happened during the Santa Rosa earthquake, if you still took that protective action, drop, cover, and hold on, you did the right thing. It gave you a chance to practice. And in some cases, you may feel shaking and you may not get an alert. There are a lot of factors involved there. You might be outside of the MMI region. You might have your location services might be slightly off. There are a lot of factors, and we generally try to dig into those. And like I said, we're always trying to figure out ways to improve what we're doing.
Awesome. Couple more here. Are there any plans to expand the scope of ShakeAlert to earthquake hazard zones beyond the West Coast? Example, the Wasatch Fault.
Yes, and of course, as I mentioned during the talk, is that our commitment is to finish the three-state system first. We want to complete the build out of the seismic networks. As I said, we're about 82% completed, and we really want to finish that off and get it done by 2025 or the end of 2025. But we are currently investing in a feasibility study with just to see the possibilities in Alaska. And that work is actually starting. There's a report that will be generated by the middle of 2024 to find out the possibilities of doing earthquake early warning in Alaska, and that would focus on certain regions of the state. But right now they're in the stage of trying to figure out if it's possible, but with no implementation date in mind. So yes, there's interest in looking at other places. But again, we're focusing our efforts in getting the three-state system completed first.
Okay, two more it looks like. Can I still get an alert if I'm not on a Wi-Fi connection? Yes.
Absolutely.
Great, easy answer. And then it looks like final question here. Let's see, did USGS work with companies like Japan and Mexico who already have these systems in place?
Yes, and what's really great about this, and I know I spoke about collaborations across the 3 West Coast states, but we are constantly talking to our colleagues doing earthquake early warning in other countries. And so the US system is most similar to the Japanese system. Canada is in the process of building their own earthquake early warning system, and we are having conversations daily. In fact, they're very involved in the work that we're doing. Canada is planning on introducing their earthquake early warning system, which will have coverage on the West Coast and British Columbia, and on the East Coast as well, sometime in 2024, sort of spring of 2024 timeframe. Okay,
well, I think that's all the questions we have. A huge thank you again to you, Robert, for your talk. A huge thank you to our audience and asking all these great questions. In case you want to watch this again or share it with others who weren't able to attend the live event, Robert's lecture will be available in about a week for on-demand viewing on our website, which is www.usgs.gov/PLS. And you can also find videos of our past lectures on that website spanning the past 20 years that we've been recording. We've been doing these for over 30 though. And on the website, you'll also see our lecture schedule for the remainder of this year. And we're already adding speakers and subjects for our schedule for 2023. And if you want it to be added to our mailing list so you'll always receive notices of upcoming lectures, please send us an email, which is wmcesic@usgs.gov, and we can add you to the list. And just one more reminder, we hope you'll join us again next month, October 22nd at 6 p.m. Pacific, for Manuel Husa's talk titled Blowing in the Wind, Science to Help Understand and Help Reduce Wildlife Impacts from Wind Energy. Thank you again, Robert. Thanks to all of you, and everybody have a really good evening. Good night.
Thanks for joining. Take care.